All right,
Okay.
all right, everyone. My name is Rohan Paldu. I'm on FRC Team 4112, the EagleBots, and am a FTC mentor for Team 14419 RoboRiders. So my partner for this presentation, who is Josh Jonathan from FRC Team 4509, was unable to attend the session due to some scheduling conflicts, but do know that his contribution to this presentation is there, and I greatly value that. So with that, let's get started. So before we begin going into the specifics of Onshape, I want to start with a sort of high-level explanation of what a typical robot designed in Onshape looks like. So at the very top, you have your main assembly. And what this is it's where your entire robot essentially lives. It's every feature, every motor, every aluminum extrusion, if every aluminum plate, stuff like that. It's it's just the view of the entire robot essentially. And then underneath that, you have what are known as subassemblies. So subassemblies are basically assemblies of individual subsystems such as an intake, an elevator, or linear mechanism, along with the drivetrain. So what this subassembly is comprised of most of the time are part studios. So part studios are what Onshape calls its part naming file system. So each one of these part studios can contain one or more of these parts in a single file. So that's just sort of a high level explanation to sort of get you guys situated into what the broader picture would be when you look into a typical Onshape document. We will be taking a look at a Onshape document of a full robot near the end where you can see this. So, all right, let's get started with our first topic, which are sketches. So the core elements of any sketch within Onshape are the sketch entities. So these are stuff that you use to create 2D objects such as various shapes like circles, rectangles, squares, uh, various size polygons. You can use them to create lines and arcs. And as you can see, some of these options have drop downs where you can choose different type, where they have different options to create a specific type of rectangle. So we'll look more into this when we get into our demonstration near the end. But for example, if this was Onshape and I were to click this drop down, I would see the corner rectangle, which is this image right here, along with the center rectangle. So I can choose based on how I want to create my part, what type of specific sketch entity to use to draw here. So that's just how sketch entities work in Onshape. And so now we get into dimensions. So what are dimensions? Well, dimensions are the main method in constraining geometry. So what does that mean? Well, what that means is that whenever you draw a shape within Onshape, it's going to show up as a blue. So let's take the example of a square, for example. So when you draw the square, it's going to be 4 lines all shaped and they're all blue. So what does that tell you? That tells you is that the computer, or well, Onshape in this case, doesn't know where this rectangle is located in space. So right now it's just sort of aimlessly there. It's not really, focused at any point. So you got to use dimensions to help constrain it. So what that means is I'm going to have to constrain the rectangle's length and width, as well as where it is located in that huge space. Because if I don't do that, it's just going to be located somewhere in space, and I'm not going to be able to identify where that is. So dimensioning is a really powerful tool, and we'll take a look at how to use dimensions along with the next topic, which are sketch constraints, when we get to the demonstration, sorry. So sketch constraints, and you can see all of them here, and we'll go through each one after just sort of broader explanation. They're helped to control geometry just like dimensions are, but unlike dimensions, you don't really see them most of the time. So most of the time, the constraints you use are known as implicit constraints. So what does this mean? Well, if we break that term up, we see 2 words. We see implicit and we see constraint. So what the implicit part means is that the user is not actively creating that constraint. Onshape is doing it while we are sketching our object, whatever that is, be a rectangle. So if we take our example of the rectangle again, if I chose the center rectangle option and I decided, I will again demonstrate in the demonstration, if I were to select that rectangle and then draw it at the origin, which is the center point of the entire sketch, I'm basically creating what is known as a implicit constraint, and that constraint is coincident. And what that is telling Onshape is that, all right, the center point of this rectangle is located at the origin. And so I, as the user, don't really have to think about it because Onshape's already done it for me. It's already constrained the rectangle in that area. So let's take a look at what the various sketch constraints are in Onshape. So we have constraint here, which is used to sort of fix it in specific points. Concentric, this is especially useful with circles, where if you want a circle directly in the center of another circle, that's where that would be used. This is the parallel constraint. So this is where if you want two lines to be parallel, you can do that. The tangent constraint, where if you have a arc or a circle and you want it to be tangent, meaning it's touching one point on the line, you can do that. There's also the horizontal and vertical constraints. So I tend to use these two a lot in my Onshape projects or art studios because they're one of the fastest to use, and they're the ones that you most often see being implicit constraints. So basically, the horizontal constraint is used to make sure that whatever you're sketching, in this case, if it's a line, it's perfectly horizontal. So if I were to put, let's say, a level, which is basically a way to check if an object is perfectly horizontal or level as its node, if I were to put a level on that line, it would show as perfectly level, meaning it's perfectly horizontal, because I applied a horizontal constraint. The same idea applies with the vertical constraint, except of course it's vertically all straight. Then we got the perpendicular constraint. So what this is used is to create perpendicular relationships between two lines. So for example, in a rectangle, all four corners have perpendicular implicit constraints, right? Because that's just one of the properties of a rectangle. It's got 90-degree angles on the inside. This is another extremely helpful constraint, the equal constraint, denoted by this equal sign here. So this is a great time saver for me personally, because let's say I've fully dimensioned a line somewhere. Let's say I've said this line is 26 inches and the center point of that line is on the origin. All right, so I know it's fully constrained. Rather than going, and I have a few other lines, right? Let's say I have 4 other lines that I want to be that same length of 26 inches. Rather than going and dimensioning all 4 of those lines individually, I can just select all of them and use the equal constraint. And because one of those lines is already dimensioned to 26 inches, Onshape will automatically make all of those lines reflect that dimension. So let's say I wanted to change that dimension to 20 inches. I can just change that one dimension and all 4 lines are. Thomas, so right now I am just explaining the ideas. You're going to get a demonstration at the very end. So don't worry about if you don't understand something completely yet. We're going to make sure that you understand it at the end, just because we are going to be doing a demonstration. So like I said, sketch constraints are another way to help constrain geometry, and they're often used in tandem with dimensions. So this is our first example for sketching. And so first, let's analyze this. What am I showing you here? Well, does any of the attendees know what this is by chance? Just type it in Q&A if you know. All right, so I'm not getting drivetrain. That is correct. This is a side view sketch of a drivetrain. So let's analyze this a bit further then. We can see that we have 3 circles that are construction lines, which I will demonstrate in in my tutorial. And basically what that means is that when I go to perform the operations that I need to turn this 2D sketch into a 3D sketch, those features in the sketch will not be included in that transition. And that'll make a bit more sense when we talk about extrusions and all of that later on. But so we can see that all of the sketch entities here are black. So what does that mean? So that means that everything in this sketch is fully constrained, except for these top 2 points here, but don't worry about them. So up here, I've included all the sketch entities and relations that I used. So let's just figure out where I used where. So I used the line constraint here to create my chain paths. So that's what these are here, and I use these to help find my center to center distance. So just a quick rundown of what that is. It's used to help make sure that you can actually create a chain that's just tight enough without tensioning to sort of make sure that you're getting enough the power is transmitted from the gearbox that's located here to the outer wheels. So that's what that is, if you didn't know. I have my outer wheels, which are these 3 big construction lines. And if you notice, I dimensioned the center wheel here to be 6 inches. So you can see that I didn't put any dimensions on the outside, and that's because I used an equal constraint on all 3 wheels. So now that all 3 wheels are 6 inches, regardless of if I were to go and try and drag it, it would not change. It would just be 6 inches. So we used quite a few different, so moving along the line, we can see that a rectangle was used, and that was used to create the drive rails. So I'll get into how to create that in my demonstration at the end. And we used, so what we had here is this little funky symbol. So it looks like it's turning a regular solid line to a dotted line and back. So what does that look like? Well, that's construction lines. So what those are used for are essentially you can turn whenever you go to exit a sketch and you want to create a 3D object from that sketch. If you were to have construction lines be the only thing, sorry, not construction lines, construction geometry be the only attribute in the sketch, meaning everything is dotted, nothing will get extruded, because what that tells Onshape is that, all right, I don't want to extrude this feature. I just want it there so I have a reference to whatever else I'm actually going to be extruding. So we can see that here with these bearing holes here. So I don't know. So it's a bit small here, but you can see them. It's the innermost circle here. And so there's 3 of them. There's one here and here, one here, and one here. They're all 1.1245 inches. Onshape defaulted it to 3 decimals, so that's why it's showing up as 1.125 inches. So again, I use an equal constraint here to demonstrate that, all right, I don't want to waste any more time, and I just dimensioned all of these here to be 1.125 inches. And I don't have to worry about, going and dimensioning each one. I just do an equal constraint and I'm good. So one more key aspect that I used was the mirror tool. So this is an extremely powerful sketching tool that you can use within Onshape. And what it essentially allows me to do is that there's this big line in the center that I just drew, and it might throw some people off because, like, wait, what is that line there for? I don't know. Why would I add that line? Well, it's because I can use that line as a mirror point to take whatever's on this side of my sketch and move it right here to the other side. Or, well, in this case, it's the other way around. I mirrored here, and I went and I got this as my result. So what this allows me to do is, if I know that 2 objects, or well, if I know that my sketch is symmetrical, let's go there, I can just draw one side of the sketch and then just draw a center line here, or use a plane or whatever, and just mirror it over, and boom, I have a completely constrained other side here. And I'll be actually creating a drivetrain at the end, so you'll get to see all of this in real time. But for that, let's move on. So now we discuss another important thing about sketching. So and that is patterns. So there are two types of sketch patterns, circular and linear. So circular, obviously, patterns in a circle, in a sort of circle manner, whereas linear patterns in a straight line. So you can see here that I've included the definitions of the two. Circular uses a center point in order to create multiple sketch entities around the center point, while linear forms multiple sketch entities into a straight line. So where would I use this? Well, let's move on to the next example and see that. So what do I have here? Does anyone want to take a guess? I'll give you a hint. The center is a motor. No, not a bearing. You're close though. I'll give you a hint that these four circles here are a wheel. Yes, that's what the outside is, but you're really close now. You're really close. So we've established that the center here is a motor and the outside is a wheel. So gearbox, not quite, but I'll give you that. So what this is it's from the 2020 game Infinite Recharge for FRC, and this is a power cell shooter essentially, and it's a sort of sketch of how that would look like. So let's dissect this, shall we? So we have three circles here. The outermost is our shooter wheel, and that is 4 inches in diameter. You can see its construction. We have our center little outer shell of our motor. So that's this 2.36 inches. Specifically, this motor is a Falcon 500. So to get that value, I went onto Vexpray's website and I got the value from their Falcon 500 drawing. And I insert it here directly in the center because I want this wheel to be direct driven from the motor. And then I have what's known as a bolt circle in the center. So this bolt circle is 2 inches, and it's essentially the 4 bolts that I want to use to mount the motor onto the plate that I'm going to be designing for this shooter. So you can see that I use the circle tool and construction geometry here just to get my shooter wheel, my motor outer body, and my motor bolt diameter, and then I use the circular pattern here, which is denoted by this dimension of 4x, to take my first motor mounting hole and sort of pattern it around 3 more times to get me the 4 motor mounting holes that I need. And you can see that I actually dimensioned this off from the origin here, which is this little dot, 3.5 inches. 3.5 inches. Sorry. So I decided to do that, and to make sure that it stayed perfectly horizontal, there's an implicit constraint between the center of these circles with the origin, which is denoted here. And then I also used a vertical constraint, and this was not implicit. This was me actually going and selecting to do a vertical constraint with this center point of the main shooter assembly with the center point of the motor mounting hole. So that allowed me to make sure that this was correct and there was no deviations anywhere. So, and then there are a few implicit coincident constraints here that were between the 3 construction circles, that I drew. So with that, we've basically covered the introduction of sketching. Now, obviously, there's a lot more you can get into, but keep in mind this is an intro class, and we're going to be focusing on the basics. So let's go into part creation. So the core features of part creation are these extrusion tools, and they take your 2D sketches and they turn them into a 3D object. So let's take a look at what we have here. We have the extrude option, the revolve option, the sweep option, the loft option, and the thicken option. So depending on what scenario you want, you're going to use a different one of these. So let's say I want to create a drive rail tube. So with that, I have my sketch of the cross section of the tube. So that's just a rectangle, and then I have another smaller rectangle in there to represent the thickness of the material. And I've dimensioned everything, and I think, all right, that's the sketch. I'm good. So now I exit out of the sketch, and I And Onshape's like, all right, here's a sketch. What do you want to do with it? So I'm trying to create a rectangular prism essentially, right? Because it's a drive rail. So I'm going to choose the extrude option. So this option is is probably the most common option you're going to end up choosing, and it basically takes that sketch that you create and sort of extends it out however many distance, however much length do you want. So let's say, all right, let's say I have my rectangle and it's sort of on the front plane. So let's say you're looking straight at the rectangle, and so I want to extrude that. So what the extrude tool does is it just brings that sketch and turns it into a 3D object, and it doesn't do any like angles. It just goes straight out from the sketch, or it can go straight back, or it can do what's known as a symmetric extrude and do both. It can go back and forward. And then another common one is the revolve. So let's say I wanted to make a shaft by hand, a circular shaft. How would I do that? Well, if I were to cut a shaft and get the cross section of it, you would see that it's a rectangle. So I go ahead and I draw my rectangle, I dimension it, everything's good, I exit out of the sketch. Now, how do I turn that rectangle into a shaft, a cylinder? Well, if you think back to geometry class, we know that if we were to rotate that a certain amount of times, we would get a sort of the appearance of cylinder, right? So that's what the revolve tool does. So I'm going to go ahead and, I would select the revolve tool, and then I would go and select that sketch and then be like, all right, I'm going to make it go 360 degrees because I want a fully closed cylinder. And then I want this, and I want the radius of the cylinder to be 0.25 inches. Let's say it's the diameter of the shaft is 0.5 inches, so a half an inch. So I do that, and I got my shaft. But the main thing to keep in mind here is just that these extrusion tools are just as simple as taking a 2D object and turning it into a 3D object. All right. So these last three things are a bit seldom used. These are a bit seldom used. I don't tend to use thicken much at all. I tend to, if I'm creating wires, for example, I use sweep for that. And then if I want to create like a pyramid type object, I can use loft for that. And we may get around to demonstrating that, but just keep in mind that the two main ones you're going to probably end up using the most are extrude and revolve. So now let's talk about the shell and rip tools. So what are these? So the shell tool basically hollows out your object and creates a wall. So what does that look like? Well, if we look at the icon, we get a pretty good example of what this would look like. So let's imagine that this cube here was completely solid, and I decide to, use the shell option and shell it out essentially. I can choose however many faces. Let's say I want to choose, in this case, they chose the top face and the front face, and they shelled the entire inside out. So now it's an open object, and this saves a lot more time than me creating the 4 different pieces and then assembling them together. So that saves time there. And then the rip tool is essentially used to create, it allows you to take a sketch of a hollowed out part where there's gaps inside of it. So think of like a gearbox plate where there's a bunch of pockets. And so we can use the rip tool to create these sort of walls of material from our sketch and sort of just have those connecting pieces. So if you imagine a bridge, a truss bridge, for example, all those connecting pieces, you could use the rip tool to create them if you were to design that bridge in Onshape. So, and an important thing to keep in mind is that these two can be used in tandem. So you can decide to shell an object and then be like, all right, I'm going to sketch something and then create these ribs here. So I don't tend to do that too often just because of some really cool features that Onshape has that we'll get into later in the presentation. But so I tend to stick to shell if I ever do use these two tools, just because there are some really cool features that I don't want to give away yet, but Onshape has them. So let's move on to fillets and chamfers. So what are these used for? So this is the best way I figured I could describe this, and it's from a manufacturing standpoint. So let's take FRC for example. In FRC, there's all these teams are using depending on the team, they might be using routers, mills, and all these machines that can't really cut uh, pointy corners just because the drill bit the bit, sorry, inside of it is when it spins, it's sort of like a cylinder. So what these are used are for our fillets tend to they sort of help make sort of compensate for the drill bit size, and they allow you to get either flat edges in terms of chamfers or sort of rounded edges like fillets. So where you would use these sort of depends on your application and your machine. So it sort of depends on who's manufacturing the part. If they say, all right, don't use fillets that are smaller than this because we can't manufacture that, it just depends on who's making the part and how they're making it. So that's important to keep in mind there. So now let's talk about a really fun thing, part mirroring and planes. So where would we use this? Anyone have any ideas from the sketch mirror that we talked about earlier? Feel free to put your guesses or answers in Q&A for that one. Copy one side. Can you specify that a little bit? I get what you're saying, but I just any symmetrical part, yeah. So that's sort of where we would want to use this we might not even use it to create one part. We can use it to mirror a single part onto another side, stuff like that. So part mirroring, what is this used for? So let's say you're designing a drivetrain. A drivetrain typically has 4 outer rails, right? Exactly. You can use the part mirroring and planes to take the left drive rail and mirror it onto the other side to get your right drive rail because they're the exact same. So, and you can do that for the top and the back even if those are the same. So you can use these to sort of save time on part creation, and planes can be used for many different things. You can create custom planes to get sketches in certain places that the top, the front, and the right plane don't exist for. You can use them for that. You can use them for a lot of different things. You can use them for mirroring. So those are 2 really sort of important things to keep in mind. And don't worry, I will be demonstrating this in the demonstration near the end. So transformations and derived parts. So I will say this before I get into the specifics of derived parts. This is highly, highly dependent on your workflow. So let's say that your workflow tends to, some teams in FRC tend to derive gears and pulleys rather than sort of assembling them together in a different file in assemblies, and they just do it all in their Part Studio file. So that's one workflow. Some teams, like ours, we tend to just do the math based on our calculations and we just do the math, and then we get to in the assembly we just place whatever part we need accordingly where it needs to go in the shaft, and then if we need spacers, which is primarily where derived parts come in handy sometimes for some people, is we would use sort of the measure tool in Onshape just to get that value, and then we go into our part studio and create that spacer. But anyways, let's do a more formal explanation of this. So transformations can be used to move parts, sketches, and sketch entities that are not fully constrained. So what does that mean? Let's say I have a rectangle that I didn't constrain, and oops, I accidentally moved it too far from the origin, and now I want to just drag that back. Well, I can use transformations to sort of move that sketch onto where I need it to go, and then dimension it and constrain it there. Can do the same thing with parts. Let's say I want to make it easier on myself when I import this part studio into an assembly and keep all my parts in sort of a centralized location. So I can use transformations to just move them where they need to go, depending on how I created those parts. So that's transformation. So let's talk about derived parts more formally. So derived parts can allow you to add parts that have been made by others. So this could be from parts libraries or other public resources that Onshape has, and you can or you can use your own parts and just sort of import them into the parts area without having to remake them. So again, this is highly dependent on your workflow, of course, and we'll get into. I'll show a few examples of where a derived part might be more advantageous than opening it in an assembly in our demonstration. So this is the next topic, multi-body part studios. This is game changing. I'm telling you, this is really game changing. It's a powerful sort of workflow that you can use to greatly speed up your assembly time. So and it allows you to have more of a top-down mindset when it comes to design. So I've said all these things about how great multi-body part studios are, but I haven't explained them yet. So what are multi-body part studios? They are these. So it's, as the name suggests, there's multiple bodies or parts inside a single part studio file. And I hinted at this at the beginning when we did our top-down explanation of how a typical Onshape document with the robot looks, and so that's what I'm referencing here with top-down design. So essentially what this allows you for is it allows you to save time in your assemblies. So let's say I have 4 drive rails, and I'll demonstrate this in the demonstration where I will be designing a West Coast drivetrain. And so I can use part mirroring to take my 2 front and back, my left side and my front side drive rails, and sort of mirror them to get my right side and my back side. So that allows me to have 4 parts all in one part studio, so that when I go to import them, I don't have to click each individual part and mate them together. I can just import, do what's known as a group feature, which we will get into later, and there, all my parts in that part assembly, if oriented properly, are all there. And that's a really, really cool thing to have in CAD. So let's move on then to assemblies. So this is where you take all those parts that you've made, which are made up of those sketches, and you take those parts and you import it into what's known as an assembly file. So here you can connect those parts, you can make those parts move in certain directions and not move in other directions. And you can this is where the simulating part, for the lack of a better word, comes from in designing a robot. So Onshape mates are a lot more different than mates than in other conventional CAD platforms like SolidWorks or Inventor, for example. In that Onshape relies on mate connectors. So what are mate connectors? So they're essentially attachment points for your assemblies. So what does that mean? Let's say I have my 2 rectangles again. I can choose the corners, the top left corner of that rectangle and the top right corner of that rectangle, and connect them. And now then I have the 2 rectangles sort of connected, adjoined by those mate connectors. So it's sort of like a screw, for example. So let's say I have a piece of 2x1 and another piece of 2x1, and I want to connect them. Well, I can use a screw I can just drill in a screw, and then I have those 2 pieces connected at that point, and they won't move, right? So it's the same sort of mindset with mate connectors. And now we move into mates. So mates are a type of constraint used within assembly. So they're sort of like the dimensions and the sketch constraints of assemblies. So the most common ones used are the fastened and revolute ones. So which are these two first ones here. And so these mates are they all connect with mate connectors. So you often use just two mate connectors on the two pieces that you're trying to connect, and you select them, you choose which mate you want to use, and boom, those two pieces are constrained how you want. So some of these can so with some of these mates, you can either constrain the object completely or you can allow for some degree of movement. So let's take the revolute mate, for example. So this mate can be used to allow something like a pulley or a shaft, for example, to spin in a bearing hole, for example, or a bearing. So I've constrained the shaft or the pulley so that it's inside the bearing, so it doesn't move around left or right or up or down, but it's able to spin and rotate. And I have that degree of movement that I can animate, and I'll show you how to do that, and sort of show how that object would move if we were to build it in real life. So now we get on to, honestly, this is my favorite tool in the assembly feature besides mates. It's the replicate tool. So this is this is a tool as seen in its name, where you can take objects that you've already mated together. So let's say a bolt and a nut, and sort of replicate them in different areas. So let's say we have drive rail extrusion, and on the top there's all these holes for rivets. And so I want to put a belly pan, and I want to use each one of those rivet holes to connect our rivet from the belly pan to the driver. Well, it's going to take a lot of time to get all of those rivets individually placed, right? I have to mate this rivet, all right, to import another rivet, mate this rivet, all right, I have to do that again and again. And it just takes a lot of time. But I can use the replicate feature here after I've mated my first rivet with the belly pan and the drive rail. Just be like, all right, Onshape, take this rivet, put it along all of these holes that I've selected, or this entire face that I've selected, and I click that check mark, and boom, all of the rivets are where they need to be, barring any issues. So it's a great tool that allows you to speed up the assembly of sort of monotonous pieces like rivets, bolts, nuts. You can use them with bearings, you can use them with shafts even if you wanted to. You can use them with virtually anything, but keep in mind that it depends on keep in mind that you are able to actually replicate the object based on your parts. That's just something you want to keep in mind. And we'll get into this when I go into my demonstration at the end here. So this is another tool that is commonly used in the assembly file, and it's the fix tool. So the fix tool allows you to sort of ground a part in the assembly and not have it move around and sort of just be floating in a vast space. So let's take the example of our drivetrain. So I imported this drive rail, and I have all of my drive rails, and I could just drag them around. I can move it up, down, left, right, but I don't want to do that. I can use the fix tool, and I can fix one of those drive rails so that that object no longer moves. So obviously what you would have to do beforehand is sort of position whatever object you want to fix where you want the rest of your assembly to sort of move up on. So it's commonly done on the drivetrain, like I've said, like I just used as an example. And so I can do that to help make sure that if I try to move my whole robot assembly or my drivetrain in particular, that it won't move and it's just fixed in that position where I last kept it. So that's just a brief sort of introduction to the assembly file. And don't worry if you didn't really understand anything. We have the demonstration to help clear that up. So now we move on to some more Onshape specific features. So I've been taught all of these things that I've been talking about. You can more or less see them in other CAD platforms, minus mate connectors. Well, actually, I take that last statement back. Well, you might not see Onshape mate connectors, but you do see some form of mate connectors in other CAD platforms. So let's move on to stuff that Onshape itself has. And let's start with Featurescripts. So what are Featurescripts? They are custom-made tools that can be used inside of Part Studios. So what does this mean? Let's say I want to make a feature script to automatically generate a drive rail for me, and there is one of these. So that's where this example is coming from. So let's say I'm too tired of extruding my drive rails out, and it's just a mess that I don't want to worry about anymore. I can go and I can add a feature script to generate my drive rails for me, and with a few clicks and some sort of inputting some parameters for how I want those drive rails to look, and just if I want a whole pattern on them, stuff like that, I can use one feature and boom, all of my 4 drive rails are there for me, exactly where I want them. So feature scripts can be used to take those really mundane tasks that, that are just sort of boring and repetitive to do and just make it super painless, super simple. And yeah, one thing I will note about feature scripts is that I would not recommend using feature scripts without learning how to create whatever you're using the feature script for manually. So let's take the example of my drive rail example. The way I would teach someone Onshape is I would teach them, all right, want you to create this drive rail, use the sketch feature, use the extrude, use the shell option or an extrude cut, which is an option under extrude to create this drive rail. And so I would have someone learn how to do that so that in the case that these feature scripts break because they are not, in case these feature scripts do break because they can and they will break at one point when you need them, you're able to replicate the test that feature script did for you and sort of not have any issues there. So that's my warning to you in regards to feature scripts, and just know how to create that part manually or how to perform that option manually without the feature script in case something goes wrong. So with that, the most prominent is feature script used in FRC and even FTC are Julia's feature scripts. So these are made by Julia Schultz. She's one of the more prominent members of the FRC community, and she's really been a great help for all FRC and even FTC teams to help speed up their workflow. So she's created a bunch of different feature scripts to help with pocketing, to turn solid objects into tubes and stuff like that. So she's really stepped up and sort of helped the community there. So the way to add feature scripts, I will show you how to do that in our demonstration. So now we get into the next sort of Onshape specific thing in version control and team workflow. So this is highly specific to your team. And so what version control is you can essentially record the iterations you make on whatever you're creating. Let's say it's a drivetrain. And so if something catastrophic or something wrong happens to that CAD file, you can easily go and say, all right, here's the copy right before that happened. We can revert back to that, and now we have our drivetrain before that catastrophic issue. So you can use version controls just to sort of help with iteration and creating and sort of just a backup of all of your stuff in Onshape. So this is highly specific to your team. Like I said, some teams decide to use it, some teams don't decide to use it. I would personally only use it on parts you're generally going to be iterating a lot on. So let's say something like a drivetrain, you often wouldn't iterate on too much. Excuse me. So you would just have that made the first time and it would probably stick. So any part that you're changing rapidly, so something that you're prototyping a lot. So if I get an example from like the 2020 FRC game, so a lot of teams were prototyping different shooters, and in CAD, they were making, and in CAD, you could use version control to keep track of those different iterations. And if you needed to go back to one by chance, you can just go find it and revert back to that, and you're good to go.
Rohan, I'd like to let you know you got a little less than 15 minutes.
15 minutes? All right, that's cool. Thank you for that. So now we move on to our demonstration in Onshape. And so with this, I'm going to stop sharing my screen momentarily. And going to open up Onshape here. And all right, so everyone should be able to see this screen here. And so what this is this is the Onshape tutorial. This is the Onshape, sorry, not tutorial. This is just the Onshape Part Studio form. So what the first thing you see is you see these three planes, your front, your top, and your right plane. So what I'm gonna demonstrate today is how to create a West Coast drivetrain from scratch. So let's get started. The first step in this is to create a sketch. And so I'm going to choose the top plane. And to do that, I'm just going to hide all of these here. And you can see that I have this little cube here. And what that allows me to do is just view this sketch from the top plane like I want to. So now I'm in the sketch part of the part studio file. So what does a drivetrain, West Coast drivetrain have? It has 4 drive rails. So I can either choose to draw those 4 drive trails and constrain them, or I can use 2 rectangles like this, one here and one here, and along with 4 lines, I can get my drive rails all drawn. So this is again highly dependent on how you do things. So with that, now that I have my 2 rectangles drawn, you can see that they're blue and they're not constrained. So let's use some dimensions to constrain them. So this is the inside. So I'm going to leave that alone for now. So the outer dimensions of this drive rail, let's just do something sort of on the extreme. Let's say 30 inches. And let's zoom out here by 30 inches. So you can see here that this rectangle, the outer side of the drive rail is not fully constrained. And you might be wondering, why is that? Well, it's because if you notice at the beginning, I used the center point rectangle and I positioned the center of that to the origin. So now everything is constrained there. So now let's do the inside. So time to do a bit of math. The drive rails are 1 inch in diameter. So with that, so we need to subtract 2 inches, one for each drive rail here, to get a inside diameter of 28 inches long, 28 inches wide. So now we have sort of the basic look of our drive rail. And you can see right now it's all one piece. If I were to extrude this, it would all be one piece, right? So to fix that, let's draw some lines. So I'm going to draw one line here to split these up into different drive rails. So there's that first drive rail here. Second drive rail here. And our third drive rail here. And so you might be noticing that I am not going up here and clicking on each object, each sketch entity while I'm doing it. And that's because that if you look here, you can see that each one of these objects has its own keybind. And so I'm just using those keybinds to help speed up my workflow, not have to drag my mouse over, click, come back, drag back, click. So it just allows me to save some time there. So I would highly suggest you guys sort of invest time sort of just practicing and, remembering, all right, that's C, all right, C is for my circle, R is for my center point rectangle, G is for my corner rectangle, stuff like that. So with that, I have my 4 drive rails done essentially. So let's use the extrude tool now to extrude all of these, right? So, all right, just select all of these, and drive rails are 2 inches tall. So let's do that, and boom. Uh-oh, we got a problem here. All of these are one piece. So that's something to keep in mind. And so what you have to do then is you're going to have to extrude these all individually. And that's going to take a lot of time, and there's going to be unwanted features. So I'm going to use one of Julia's feature scripts here, the extrude individual feature script. And just so you know, to add feature scripts, you could come down. Usually for you guys, it'll probably be up here, but for me, it's all the way down here. You can click add custom features, and let's just search up Julia feature scripts here. You can see that, all right, so you can see there's Jeffrey's, there, Julia's feature scripts. So we can just click that, and boom, all of those will be, you can click that, And you can add all of these feature scripts that she has. She has a lot of them. And so she's not the only one. Keep in mind, there's a lot of other people in the community making feature scripts. So you can check Chief Delphi or the FRC Discord for that. It's most likely going to be on Chief Delphi. So anyways, let's use the extrude individual feature script. So what this allows me to do is it fixes the problem that I had earlier, in that I can extrude all 4 of these sides individually all at once. So I don't have to do 3 different extrude, or well, 4 different extrude operations, and I get all 4 of my drive rails done like that. So boom, 4 drive rails, just like that. There's an even easier method. I don't have to even sketch anything. What is this, you might be asking? It is the West Coast Drive tube generator feature script. So what this allows me to do is, you can see here that it shows the front rail and the back rail. So let's say I want the top bar to be 30 inches, the sidebars to be 30 inches. There would be no offset, so they're perfectly like that. And so, ooh, that's nice. It tells me that it's over the size limit. Well, that's okay. We'll ignore that for now. And so I selected the full frame option, center gearbox, wheel drop. This is, again, highly dependent on how you guys do things in your teams. So these might change depending on what you're doing. Let's say it's a fixed bearing block. So let's say no cam, and we have all of these circles here. Wheel size is 4 inches. Slot radius 1.1252, right? Come on. All right, so that should be good. And boom, 1 feature script, all of my drive rails. But you might be wondering, hey, all of these are still solid pieces. Another one of Julia's feature scripts is going to come in handy here, the tube converter feature script. So here, we just select all of these features. And for now, I'm going to not choose a hole pattern, which are these sort of holes for rivets here, or bolts even. So I'm going to select all 4 bars here. And so there we go. So, forgot to show something here. So I chose the wall thickness here, which is the thickness of from the inside to the outside here to be 0.125 inches. So let's say I want that to be 1/16 inches. 1 change, and boom, it's already fixed for me. So those are our drive rails. Now we have a few more things to add here. We have to add our wheels and our gear and our gearboxes. And just because we are running short on time here, and I want to make sure I introduce this last thing. I should probably show you guys how to do that. So I just went down here and I chose create assembly, and I have my assembly here. So I'm going to go up to the insert option, and you can see that I can choose to insert all of these individually. But why would I do that? I can just insert all of them at once because I know that I'm going to be using all of them once, all of those, and I want them to be in the positions where I created them in the part studio. So click the check mark, we're good. But if I were to move all of these pieces, you can see that they're not constrained at all. Now I could go in and use mates, but I will use this group feature here. So what that allows me to do is say, all right, all of these drive rails are now one object, essentially. So no mates, just got all of those constrained. So let's say I want to insert a bearing. How would I do that? Because I don't see one here. Well, I'll go up to the insert option, choose other documents, and I can look inside my Onshape. So I can find a gear, whatever I want from my Onshape files. Or I could use a parts library that is public, known as MKCAD. So this is run by a few of FRC alumni, I believe. And so if I just go and search MKCAD, it should pop up. There we go. So all of these things here, bearings, sensors, spacers, pulleys, Versa gussets, Versa tubes, pneumatics, fasteners, motor hubs, motors, electronics, gearboxes, all of them are there for me. But I'm curious but I need motors. I need bearings. So I'm going to go down and I need half-inch hex, 1.125 inch radial flange bearings here. I'm going to go insert that one. And I also need a gearbox. That's pretty important, I think, because that lets me transmit power. I'm going to go down, go to the gearbox option, and I'm going to go to assemblies. And let's choose this one, the West Coast Parts single speed gearbox assembly. So now we got our gearbox inserted, and let's just keep it at that for now. So
Rohan, a couple more minutes.
got it. Thank you. So we can see that we have these mate connectors, that's what these look like. And so I don't want to see those. I can just right click, hide all mate connectors, and boom. So now I'm going to show you how to mate these two to the drive rails. Let's go ahead and select the fasten mate because these are not going to be moving in any direction. So select the inside of this flange here. You can see that the corresponding mate connector is being popped up here. So let's go to our center gearbox. Choose, since I know the flange is going to be touching the outside, I'm going to choose the outside of the center here. Oh. Turns out I got to flip that, and it turns out that my center wheel is just a bit too big. My center hole is a bit too big. That's no worries. Can go in here, edit. Center gearbox, wheel drop center, center difference, slot radius. That will not be needed. Wheel size. All right. So let's just check this one more time. So notice that I clicked here down here, it shows my diameter. It's 1.5 inches. Not quite what I need, but it's all right. Oh, that's not what I wanted to show. All right. So it's not quite what I needed, but in a perfect world, this is why I say that you need to know how to make these features on your own. So like that. And I'm going to really quickly just mate this gearbox into place because we are running out of time, unfortunately. And I'm going to rotate, flip, rotate again, and click solve here. And you can see that everything was placed. So you can use these three things to help position your object correctly. And boom. So this is as close as I'm going to get, it looks like. And so that sort of shows you the bare minimum of what you guys need to know and how to use Onshape. And so we got 2 minutes, so I'm going to stop sharing my screen. And any questions, please put them in the Q&A. So anyone have any questions, any at all?
All right, great job, Rohan. Wanted to tell everybody thanks for attending, and Rohan, thanks for the presentation. The next sessions will be starting in just a few minutes, and I think everybody has the link that you used to get into here so that you can go back and go to the first Georgia First Symposium page in the email that you received from Eventbrite and be able to click into your next session. Guys, thanks again for coming, and I hope you enjoyed it.
Yeah, thank you. Thank you, everyone. I know